Okay, so we're going to continue our work with the Laplace transform. Now, last time we reminded ourselves of the definition. So you can see the definition, definition 2.1 at the beginning of the chapter. So the Laplace transform is an integral transform which you can apply to a function of a single variable t. And if the function has certain properties which amount to the fact that it doesn't explode in value really, that it doesn't increase in value any faster than an exponential, then its Laplace transform will exist. And the Laplace transform is a function of a new variable s, which appears in the definition there, the parameter in the exponent of the exponential, e to the minus st. So it's a function of a new variable s. And our chief interest in it is that it's going to provide a method for solving certain types of linear ordinary differential equation. Okay. Now, last time we reconnected with the definition and we spent a bit of time proving some properties of it. And just very quickly name those properties that we proved. We proved, first of all, basic property that the transform was linear. So this curly L notation is representing the Laplace transform. You take the Laplace transform of a linear combination of functions. That's the same as the corresponding linear combination of the individual transforms. So it's linear, and it's linear because integration is linear. Okay? That's where it gets its linearity from. We then had a property about what happens when you differentiate the transform. The capital F here represents the transform, the Laplace transform of the function little f of t. When you differentiate that, you get the negative of the transform of t times f of t. So there's a nice relationship there between differentiating the transform to get a new function of s, and this function of s is the transform of a nice closely related function to the original f, t times f of t. Okay. We explored various consequences of that. But the main, or what seems to be the most obvious important property for dealing with differential equations is this one, about how the transform operates on the derivative of a function. Okay. So we proved this last time, where little x is a function of t, and we suppose it has a Laplace transform of x of t. And then the question is, well, how does the Laplace transform of the derivative of x look like? Okay. And it bears a very strong relationship to the Laplace transform of the original function x. Transform of the derivative of x is s times the transform of x minus this constant term, which is the initial value of x, the value of x at t equals 0. Okay. So that's where we ended last time by proving that. So we'll pick it up now. We'll just look at one corollary of that result, which is about getting the Laplace transform of higher order derivatives. Okay, and that can be done by simply iterating that previous result about the Laplace transform of a single derivative. Someone's got this upside down. Ugh. Apologies, it's projecting upside down for some reason. So let me try and fix that. Good question. How do I fix that? Sorry about this. Anything there look like rotating the image? No. Power. Right. This might break it completely. Right, okay, it might be faintly ridiculous, but I'm just going to do it anyway. Yeah, I am going to turn my back to you. It's the only way to do it. Right. Okay, so excuse me for being rude, turning my back to you, but what can I do? Okay, so we're going to look at the corollary of that transform of derivative property. So the transform of derivative property tells you how the transform of a derivative of a function behaves, but the corollary to it, the corollary to result theorem 2.3, well, we ask ourselves, for instance, what's the Laplace transform of the second derivative of x? Okay, the Laplace transform of the second derivative of x. Now, we don't need to go and prove a whole new result for this. Remember, we proved the original result by looking at the integral definition of the transform. And we don't have to go and do a similar result to that, because we can just iterate the results we have done. Because the second derivative is, of course, just the derivative of the derivative. Okay? Second derivative is just d dt of dx dt. So now we're going to apply the result twice. Okay? So we can take theorem 2.3 and apply it to this situation, where we're taking the Laplace transform of the derivative of some function. We just ignore the detail of what's in the brackets here, and we just see it as the Laplace transform of the derivative of some function. So we just apply theorem 2.3, and this says this is going to be s times the Laplace transform dx dt, because that's the function in the brackets here, minus the initial value of dx dt. Okay. Well, we can see an opportunity here to apply theorem 2.3 again, because in this term here, we've got the Laplace transform of the derivative of x. So we should apply theorem 2.3 again to get that back to an expression involving the Laplace transform of the original function x itself. So this is by theorem 2.3. And so this becomes s times the Laplace transform of x of t minus x of 0. And we've still got the initial value dx dt evaluated at 0. So we can multiply that out, and we get an expression s squared times the Laplace transform of x of t minus s times x of 0 minus dx dt evaluated at 0. So this result we're looking at here, this result down the bottom, so the Laplace transform of the second derivative is all of this. If you compare that to the statement in the corollary, you see the statement in the corollary is the general statement for a derivative of any order. We see that this is the case of that special result for the case of order 2, where n equals 2. So this agrees with the form. Sure. This agrees with the formula. In the corollary when n is 2. Talk about the second. And if you want the third derivative, what's the third derivative of, what's the Laplace transform of the third derivative going to be? Well, you can just apply the result 3 times. But we just need to apply it one more time. Okay? Let's just look at that. And we'll move on when we've looked at that. Okay. What about the Laplace transform of the third derivative? Well, of course, the third derivative is just the derivative of the second derivative. So here we're looking at the Laplace transform of the derivative of a function. So straight away we can apply theorem 2.3. Because we're taking the Laplace transform of the derivative of something. So this it must be s times the Laplace transform of the second derivative minus the second derivative evaluated at 0, the initial value of that. So that's by theorem 2.3 again. But this Laplace transform of a second derivative well, we've just worked it out. That's what's in our red box there. Okay, it's all this expression here. So I just need to multiply this all by s. So I need to increase the powers on s here. Got it. S cubed, this term here, minus s squared x of 0 minus s times the initial value of the first derivative. So that's s cubed, the Laplace transform of x, minus s squared, initial value of x, minus s, initial value of the first derivative, minus the initial value of the second derivative. Okay, so the last initial value in these expressions doesn't have any s on it. And then the previous ones, counting down to the initial value of x, they have increasing powers of s on them. And then the highest power of s attached to the Laplace transform of the function x itself. Okay, so those are the first two cases of the corollary. And you can see that by induction you could establish that general formula there in the notes on page 45. Okay. So you can prove the general corollary using induction. reminds me of the old Catholic Mass. I think they changed it when I was born, but it used to be before Vatican II, which happened sometimes in the 50s or something. The Mass, as the priest used to stand with his back to the congregation. Just popped into my head. I don't know why. Anyway, maybe there's something to it. Why did I come out here? Okay. Now we have a good understanding of how the Laplace transform behaves on derivatives. Okay. Okay, in theorem 2.3 and this corollary. So we're ready now, I think, to go on and start looking at some differential equations and how we can use the Laplace transform to solve those. Okay. So there's a kind of few-step method. Method of a few steps. I've kind of numbered them. I've given them 4 steps here, but you know. So this is on page 48. So we're going to be, the typical situation here is we're confronted by one of these, by a differential equation. It could be of any order. There could be some high order derivatives, but it's going to be linear, meaning none of these derivatives of different order are multiplied together, and none of them are raised to any power. So the left-hand side here, remember the original, the unknown function y itself, you can consider that the 0th order derivative. You got a 1st order derivative and maybe up to an nth order derivative. Constant coefficients, so these numbers ai are constants. The term not involving anything to do with y can be non-constant. That can be a function of the variable t. But we must know how to take its Laplace transform in order to perform this method. So the linearity is as I've defined it there, or another way to think of it is that the left-hand side of this equation you see is the result of applying a differential operator to y. Okay, it's the linear combination of the various derivatives of different orders applied to y. So that operator is a linear one in this class, in ODEs that look like this. So so here there's 4 steps outlined which describe the method. So, and this calls back to when I first introduced the Laplace transform, and we examined the kind of related idea of using the logarithm as a transform to take problems involving exponentiation and multiplication and convert them into simpler problems involving multiplication and addition. So we begin by taking the Laplace transform of the whole equation. Okay, so just taking curly L of both sides of the equation, putting them equal to each other. And break that down as much as we can by taking the Laplace transform of the specific functions we see. The function y is unknown to us. We're trying to find y, so we don't know what y is, but we will be able to apply that theorem 2.3 to replace the Laplace transform of these various derivatives with how they relate to the Laplace transform of y itself. So you transform both sides of the equation. Now, initial values of the function y will crop up in various places, you see, because they crop up here, initial value of x, initial value of the derivative of x, etc. So anywhere those initial values crop up, we typically will be given those initial values as part of the problem, okay, if we are. So if you do have those initial values of the unknown function, then you can substitute those in at that stage. So then at the end of stage 2, you'll have not a differential equation now, but a kind of an algebraic type equation. In the unknown, and there'll be a single unknown there, which will be the Laplace transform of y. There'll be loads of s's of various powers around and the other functions of s. So you solve that resulting function for y bar. So y bar here represents the Laplace transform of that unknown function y we're trying to find. So we solve the transform problem. We get a nice expression involving s for y bar, for the Laplace transform of our unknown function y. And then there's just one last step to do, is to take the inverse transform. So the end of step 3, we'll have an expression for y bar as a function of s, and we then use the table of Laplace transforms and other results about the transform to perform the inverse transform and to get back the function y of t, which would be the solution to the original problem, the original ODE. Okay. So let's straight away look at an example. Now, the first example is pretty much all the steps are in the notes, so let's just step through that in the notes. And then I've got another example to do on the screen as well. So here's our first example. It's a second order differential equation in y, d2y dt squared minus 5 dy dt plus 4y plus 12. Okay, nice linear equation. And we're given these initial conditions, these 0 initial conditions, that both the function y and the function, the first derivative of y, so we're using this dash notation here for derivatives, that those two initial values are both 0. So we go through those steps we've just outlined. Okay. First of all, we take the Laplace transform of both sides of the equation. Looking at the right-hand side first, the Laplace transform of the constant 12. Well, remember, the transform of the constant function 1 was 1 over s. The transform is linear, so the transform of 12 will be 12 times the transform of the constant 1. So the transform of 12 is 12 over s. Then we take the Laplace transform of the left-hand side to form the transformed equation. And first of all, we're using linearity, okay? Because we have to take the Laplace transform of this linear combination of these three things. So first of all, we say, and it's not said explicitly there in that solution, but we're using the linearity. So saying the Laplace transform of the whole left-hand side is the Laplace transform of that minus 5 times the Laplace transform of that plus 4 times the Laplace transform of y. So we're using the linearity. But each of these things are either the function y itself, which we're trying to find, or derivatives of y. So we can use that theorem 2.3 we just talked about there and its corollary. So how do we use it? Well, you see, we have to introduce y bar into our equation. Y is unknown to us at the moment. Ultimately, we're trying to find y. So we don't know what the function y is, so we don't know in any detail what the Laplace transform of y is. Okay? So we just denote the Laplace transform of y using this notation here, y bar. Okay? Remember, there's a few different notations for the Laplace transform. I could use a capital Y here, or I could use the curly L of little y. But this bar notation is perhaps the most efficient, just in terms of writing it down on the page. So the Laplace transform of 4 times y becomes simply 4 times the Laplace transform of y. The Laplace transform of the derivative of y becomes s times the Laplace transform of y. So s times y bar minus y0. So y subscript 0 is a notation for the initial value of the function y. Y subscript 0 is standing for y evaluated at 0. And that gets multiplied by 5 because of this coefficient 5 there, minus 5 times all. Then you take the Laplace transform of the second derivative of y. Okay, so applying that first instance of the corollary. We get s squared times the Laplace transform of y minus s times y0, the initial value of y minus y1. And here the notation y1 is standing for the initial value of the derivative. Okay. So this is the end of the first step. We've transformed the whole equation. Okay, so there's no longer any derivatives around. The only unknown thing we have now is the transform of the function y. Well, that's really the only unknown thing, is that there are these initial value constants, but we've been given value for those, which we'll put in shortly. So now it's just a function in the single unknown quantity y bar, which we then proceed to solve. So we put in the initial values. When you put in the initial values, y bar, or the transformed equation, looks like this. And then you solve for y bar. Now you can see that it's how to solve this equation for y bar. It's quite straightforward. You've got 3 terms on the left involving y bar, so you just factorize the left-hand side and divide across by the factor that's multiplying y. Okay. So you get the solution of the transformed equation as being y bar equals this rational function of s. Okay, 12 over s times that quadratic polynomial, s squared minus 5. Sorry, there's an s missing there. S squared minus 5s plus 4. Then an s there. It's present up here. I just mistyped it. So we've solved the transform problem. So we're now just one step away from getting the solution to the original ODE itself. Okay? So we now have to take the inverse transform of this. Okay? An inverse transform of this. Now, typically that involves looking down the table of Laplace transforms and searching for a function which matches this. Now, when you look at the table of Laplace transforms, a few pages back, you see there's nothing that exactly matches that form. There's nothing which has a cubic polynomial in S in the denominator. Okay? So we need to do some preparation of this before we can actually read off what the inverse transform is. And the preparation here involves converting this single rational function into a linear combination of simpler ones. Simpler meaning the degree of the denominator is smaller. So, in other words, that's the partial fraction expansion of that of this rational function here. So you've got a constant over a cubic in S. It should be possible to express that as a linear combination of simpler rational functions with a smaller degree polynomial in the numerator. So what you do is you look to factorize the denominator. Now, luckily, this one factorizes fully as it's a cubic, and it factorizes as the product of those 3 factors, s times s minus 1 times s minus 4. And so we look for the partial fraction expansion of this. Okay? Now, typically, that requires a little bit of work, a little bit of side calculation to figure out what these constant values should be up here. Okay, but you perform that. So 12 over this has this partial fraction expansion. So this is y bar is a linear combination of functions of s, and each of these now can be found on the tables. And we can use the table of Laplace transform to read off the inverse transform, to recover the original function y. See, up here we have y bar equals this. When you take the inverse transform of y bar, you get the original function y of t. You take the inverse transform of 3 over s, that goes to the constant 3. And these expressions, a constant over s minus a constant, they both come back to exponentials. You've got e to the 4t and e to the t. And the extra minus 4 coefficient on the e to the t. So we're using there again the linearity of the inverse transform. Okay. So we get this solution. This is our solution to the original ODE. Okay. So that's a good illustration of the various steps of the Laplace transform method. So let's do another example now. Put it down up here. We'll do this next example, which is suggested in the notes. dy dt plus 2y equals 4. Okay, so this is example 2.7. Okay, so the first step will be to take the transform of the whole equation. Yeah. Okay, so first we transform the whole equation. I'll make it very careful step by step. So we're literally taking the transform of the whole left-hand side and putting that equal to the transform of the right-hand side. The transform of the constant 4, we know, that's 4 over s. And then, well, the first step, we'd use linearity to break down the left-hand side. Okay? The transform is linear, so the Laplace transform of this sum will be the Laplace transform of dy dt plus 2 times the Laplace transform of y. Okay, so that's using linearity there for the left-hand side. Well, you see, y is unknown to us. The whole enterprise is trying to find the function y that satisfies that differential equation. So here we got the Laplace transform of y. So we can't simplify that in any way, because we don't know what y is. So we'll agree to just we'll just use the simpler notation y bar now for the Laplace transform of y. Just makes it easier than writing L curly brackets y all the time. So we'll use the notation y bar, but then we can have the associated representation for the Laplace transform of the first derivative of y. Okay? So using theorem 2.3, the Laplace transform of the derivative of y is s times y bar minus the initial value, y of 0. Okay. So we now have that equation. Were we given the initial value in the problem? Yeah, we were told the initial value of y in the problem was 3. So this now becomes sy bar minus 3 plus 2y bar equals 4 over s. Okay, so that's using the initial value of y to be 3. So we've gone from our original differential equation to this equation involving the y bar. Now this is the nature of this equation is kind of simpler. It's no longer a differential equation. There aren't derivatives of different orders here. Okay? There's just a one unknown quantity, y bar. It's multiplied by constant or the variable s. But now we just do that third stage within the numbered stages there, which was to solve this for y bar. So make y bar the subject of this. So you have to take the minus 3 to the other side, and you have to divide both sides by s plus 2. So it's 4 over s times s plus 2 plus 3 over s plus 2. Okay, that's a pretty good solution for y bar. So we're now kind of at the end of step 3. So this is the solution for y bar. So we now just have to take the inverse transform of this. So for this stage, what we're looking to use is the table of Laplace transforms, back on pages 42. So you're looking down the right-hand column there, and you're looking for functions like this. Well, we can see the 3 over s plus 2. That's going to be an exponential. We've got the expression 1 over s plus a. That comes back to e to the minus at. But we don't see anything immediately like the 4 over s times s plus 2. Okay? We don't see anything that matches that. So for this one, to treat this term, we're going to have to find the partial fraction expansion of the 4 over s times s plus 2. Okay? Because there's nothing on the table of Laplace transforms that matches this first term here. Okay? We need to get partial fraction partial fraction expansion of the 4 over s times s plus 2. So our y bar is going to be some constant alpha over s plus some constant beta over s plus 2. And you've got this 3 over s plus 2 still at the end. We will probably combine this with this one here after we've determined beta. So we just need to figure out what these coefficients alpha and beta. Now sometimes partial fractions, it can require to do big side calculation and solve a system of linear equations. But I mean, when there's only two unknown coefficients, it's normally just look at it in your head. So you're asking yourself what values of alpha and beta, when you combine these two again to a single fraction over the common denominator s plus s2, what values of alpha and beta will result in a 4 appearing there? Well, I think it's going to be 2 over s minus 2 over s plus 2. And you have 2 and minus 2 there. So when you combine that together, you're going to have 2 times s plus 2. So you have 2s plus 4. And then you've got a minus 2 times s. So that cancels the s's, and you're just left with 4. Okay. So we can combine those two then. So this is 2 over s plus 1 over s plus 2. Okay. Sorry, that's y bar. So this now is our final expression for y bar. Okay, it's equivalent to this expression up here, but it's now in a form where it's clearly a linear combination of Laplace transforms that we can find on the table. So the final step now to obtain the solution y of t for the original ODE, we take the inverse transform. Inverse transform of both sides. So this will imply then that, well, when you take the inverse transform of the left-hand side, you just get the function y of t, because y bar is the transform of y. You take its inverse transform, you just get back to y. And the transform of 2 over s is the constant 2, and the transform of 1 over s plus 2 will be e to the minus 2t. Okay, so barring any errors I made there, that should be the solution to the differential equation. You should always verify these. First of all, we just check that, does this have the required initial value? Remember, we were told in the question that the initial value of this function was 3. And when you substitute t equals 0 here, you do indeed get 3. You get 2 plus e to the 0, which is 1. So you indeed get 3, and then you should also go back and just check that it does indeed satisfy the original differential equation. The derivative of y is minus 2 times the exponential, and then we're going to add it to 2 times y. So when you got minus 2 times the exponential added to 2 times y, you get plus 2 times the exponential. So the exponentials cancel out, and you're just left with the 4 on the left-hand side, and the right-hand side of the ODE is 4. So the ODE is indeed satisfied when you substitute this function. Verifying against the original ODE. We confirm this is correct. Okay, any queries about any of the steps there? So we've seen 2 examples. And is there any of the steps I could clarify for you, or? Any extra comments you need on that? Now, I'll be doing a lot more work with these. We'll look at real proper examples of situations in engineering or physics where these types of equations might arise. So we'll study them in some context as well. I will also look at some other classes of functions, new functions which you might not have met yet, which we want to bring into the picture and be able to solve ODEs involving those as well. But for the moment, the next question, page 51 there, the next set of exercises. So as well as working on completing exercises 2.1 a few pages back, the first question here is open up to you now. So you've got 4 examples there of differential equations, so you can be working on those, and tutors will probably do 1 or 2 of those in the tutorial this week. But you should be attempting all of those, as well as finishing off exercises 2.1. And when I see you next week, then we'll continue looking at this and look at lots more examples. Okay? Okay, we'll leave it there for today.